Thank you so much. I hope everybody can hear me okay. Thank you so much for that lovely introduction. I'm really sorry I can't be there in person. I was very much looking forward to the conference, and I know that everybody's appetites for virtual presentations are starting to dwindle. Unfortunately, I tested positive for COVID last week, so I figured this was better than coming to a crowded room of people. But thank you so much for joining me for this presentation virtually, and I'm really excited to virtually be here. And thanks to the organizers for accommodating a change at the last minute. So today I'm going to talk about some of our recent work on using machine learning for simulation. So machine learning is in general useful, or sorry, simulation is generally useful for a large number of really diverse real world and scientific applications. These include problems like forecasting, if you want to determine the path of a hurricane or what the effect of some political action might be. Problems in basic science, like considering the minimal principles that enable insect flight, or engineering and design applications, like considering how some reactor design might enable a different kind of yield, or how efficient a particular airplane design might be. So the way these simulators often work in practice is that the relevant scientific discipline, whatever it might be, will supply us with some equation for the dynamics. And we will solve these or approximately solve them in order to predict what's going to happen. And some of the challenges these face is that they might require a lot of expertise to produce, domain-specific expertise for a particular discipline. They can be really inefficient to run, particularly if the equations are complicated. And they might not be optimized for supporting some downstream optimization process, particularly in the case of engineering and design. So we're interested at a high level in understanding how machine learning can be useful for augmenting simulation. We're hopeful that machine learning represents a promising approach to producing simulators that are more efficient by distilling the dynamics of classical simulators into an architecture that can run more efficiently, are differentiable and therefore support certain design optimization problems downstream, and can be learned from real world data and therefore might not require the same kind of expertise to produce that classical simulators require. So in part 2 of my talk, I'm going to talk about some of our work on the latter, where we're studying differentiable learned simulators and seeing how they fare for engineering and design optimization problems. And in the first part, I'm going to talk about some of our work using machine learning to produce simulators that are more efficient. I don't have any work specifically on the real world data aspect to talk about, but I think one thing that is useful for keeping in mind is that this approach could in principle be applied to that kind of data. And that's one thing that motivates our long-term vision for using machine learning as a simulation approach. So in part 1, I'm going to talk about our work using learned coarse models for efficient turbulence simulation. As in before, turbulence simulation is useful to a large number of different fields, aquadynamic or aerodynamic engineering, predicting how weather and forest fires will unfold, and understanding various turbulent basic science phenomena. This work was a collaboration with astrophysics researchers at Flatiron, where the turbulence simulation problems are particularly challenging. You need really high resolution and very large simulations in order to capture the astrophysical phenomena that our colleagues are interested in. So efficient turbulence simulation is really important in these fields. Turbulence in general refers to fluid dynamics that undergo chaotic changes in pressure and flow velocity. And it's this chaotic nature that makes turbulence very hard to predict and hard to simulate in general. So for the applications that require turbulence simulation, these are typically performed with advanced numerical solvers that are very powerful. They're often very good at predicting what's going to happen, but they're computationally expensive. Excuse me, and often cannot be run at low resolution without producing qualitatively different results. So the main question that we're interested in today is if fully learned simulators can capture complex and chaotic turbulence accurately, even when run at low resolutions. So to outline our approach, first, we're going to use a classical physics simulator to produce high resolution trajectories. And then we're going to downsample these trajectories in both space and time to produce our training data. And then we'll train a neural network to do next step prediction on these low resolution frames that were originally produced with a high resolution solver. So this is what that will look like. We're training a neural network to predict the difference between a frame at time t and time t plus delta t. To evaluate how well our model does, we're going to roll out a trajectory with our next step simulator for tens or hundreds or thousands of steps. And in order to stabilize these really long rollouts, given we're only training to predict a single time step into the future, we're going to add Gaussian noise during training. And as I'll discuss, this has a stabilizing effect, which helps our rollouts maintain stability over long periods of time, generally a real challenge with learned simulators. So in terms of architecture, oops, sorry, it's a little bit of a delay. In terms of architecture, the model is not specialized specifically for turbulence, and we're going to use the same architecture for each environment. And it consists of a convolutional neural network, a CNN encoder and decoder, as well as a processor, which is comprised of dilated CNN blocks. So this is what these look like to go into a little more detail. We use dilated convolutions to introduce space between elements of the convolutional filter in our processor. And this has the effect of increasing the width of the convolutional filter without increasing the number of parameters, and while still preserving the image size and the local structure. And then what we do with these dilated convolutions is that we arrange them in a U-shaped stack. And this means that the dilation rate is gradually increased from 1 to 2 to 4 to 8, and then decreased back down 4 to 1. And this allows us to do multi-scale processing inside of each of our processor cores. And there's going to be 4 blocks that look like this, that have this U-shaped stack from small to large scale. So we train this model in a variety of really characteristically different types of turbulence that are relevant to different domains. In the top left, we have the KS equation. This is a classic equation for unstable chaotic dynamics in one dimension. It's not technically turbulent, but it has the same kind of chaotic dynamics, and it's a very classical thing to simulate. In the bottom left, we have 2D incompressible turbulence, which is useful for capturing atmospheric and oceanic dynamics. And then on the right-hand side, we have 2 different domains that are simulated with Athena++, which is a state-of-the-art astrophysics simulator. And these are 3D turbulent simulations with compressible turbulence. That's why we have density and pressure as well as velocity for these. And the top one is uniform compressible decaying turbulence, which is ubiquitous across astrophysical phenomena and is useful for understanding black hole formation and how galaxies form. Whereas the one on the bottom is particularly useful for understanding how heat is pulled from surroundings during galaxy formation. It models what happens when you have 2 fluids traveling in opposite directions with really different velocities. And we can see across these different domains, we can qualitatively capture what the turbulent dynamics look like using the same model. And this is something that we were pretty excited about. If we look quantitatively, we can compare to the physics-based simulator, Athena++, run at low resolution to see how our learned model is doing at low resolution compared to the classical approach. And we find that we see lower pixel-wise error for the learned model in blue compared to the classical simulator at the same resolution, which is shown in orange during the training window. We also look at an intermediate resolution classical simulator, Athena at 64, and this is something that we don't beat for pixel-wise loss. If we extend the rollout to include frames not seen during training, we see that the learned models in blue, each line is a different seed, can kind of keep up with the coarse classical simulator, but eventually towards the end start to really diverge. And then if we look at a different type of signal, the spectral loss, basically how well is the power spectral density maintained for these different simulators, we see that this is where the learned model really shines. And it beats both the same resolution and the intermediate resolution classical simulator and maintains its advantage for most of the generalization window shown in pink. We can see why this is if we look at the spectrum and at the images for the final frame of the training window for each of these models. We see that the learned model can preserve the high frequency structure that the classical simulators start to smooth away in order to maintain accuracy. So on the far left is Athena at low resolution, and you can see it's a very smooth signal, whereas the learned model on the far right captures some of the sharper signal that's characteristic of the ground truth that's next to it. So this is something that we were really excited about, that the learned model is capable of keeping this high frequency structure even across learned rollouts and sort of preserve what's lost when you run these simulations at low resolution using the actual physical equations. These models, the learned model is also in some ways more efficient than the classical approach. We see that in terms of running time, the learned course model can produce trajectories that are 1,000 times faster than the ground truth if running on a GPU. The classical model is not running on a GPU and most likely would benefit from GPU acceleration, but this takes specialized engineering effort, whereas the learned model can just exploit advances across the board in applying learned models to GPUs. And then we also see that if we compare CPU times, the course model is still a lot faster than the solver at full resolution. And this is because the timing of the ground truth solver scales as power 4 with the resolution. And so if we're able to use this spatial and temporal coarsening with a learned model, we can exploit much faster times. Excuse me. We also found that across domains, this simple and somewhat domain general learned model can quantitatively match or outperform other more complex, more turbulent, specialized, and more heavily parameterized models. So this is a lot of information, but basically the high level is that our models, which are in dark blue and light blue, quantitatively outperform these other models that are also fully learned, but have architectures that have been optimized for turbulence. However, we also find that all of the learned models do qualitatively pretty well on this problem. So even though this simple and less parameterized model gets quantitatively less error, and that's something that we're excited about, in general, we kind of concluded that learned models are a generally good fit for this problem. And we see that all our models have videos that plausibly match the ground truth. So that's something that we also are just kind of interested in as a long-term thought about how these models are a good fit for these domains. I also mentioned earlier that we introduced training noise to help with stability. And this has the effect of increasing the one-step error because now the model has to denoise the inputs going into it. And you can see this at the bottom, that the noise runs have a higher one-step error in red compared to the no noise in blue. But this has a really transformative effect on stability. And you can see that the models that are trained without noise can be really unstable and diverge pretty catastrophically. You note the y-axis is going up to 10 to the 18th. So that's a really catastrophic error. Unless you think this effect is subtle, we can also look at what it looks like in videos. And you can see it really does fail quite catastrophically. I can show that one more time. It really gets pretty extremely incorrect. And the reason for this is that as the errors accumulate, eventually it will reach a regime that's out of distribution for the learned model, and then it really goes haywire, and that's when you get really huge errors. And then another thing that we can do with these learned models is train the learned models on larger time steps while still having not a huge increase or qualitative change in the error or the appearance of the rollout. So these are all models that have been trained at different temporal downsampling factors, and we see they look pretty similar. Another added bonus of this is that larger time steps cause larger one-step they cause larger one-step loss because you now have a harder one-step prediction problem. You're predicting further in the future, but you need fewer time steps now to produce a rollout of the same length. And this can lead to greater stability because there's fewer opportunities for errors to accumulate. So we see that there's actually, even though there's monotonically increasing one-step error, the rollout error actually has a U-shaped curve because to some extent, fewer steps can help with the rollout stability. And then finally, one thing we looked at was generalization to different initial conditions. Generalization is naturally a challenge for deep learning. And so we wanted to see how our models could do. So these lines shown here are the two Athena models. One is the intermediate resolution, which has a lower error than the comparable resolution one, which is shown in light gray. And we can range the initial conditions according to the parameters that are used to generate them, which happen to be from more compressive to more solenoidal. And we find that on one side of this, generalization is pretty good if we compare to the comparable resolution Athena, but on the other end, it's really bad. And we're getting really bad generalization and very variable in this regime. One thing that we noted, though, is that adding really simple constraints to the loss could help limit the generalization error. And so that's what this line in blue is. We're just preserving the total energy. And this can help limit but doesn't really make it comparable with the classical model. So we think one direction to explore is going to be inductive biases that help these models generalize, which is not something they're naturally disposed to do. So the conclusions from part one, we find that we have domain general coarse-grained learned simulators that can capture a variety of types of challenging turbulence. They outperform classical models in terms of accuracy and speed, and they're especially good at preserving high-frequency information. We also have some recommendations for stability and generalization. We find training noise and temporal downsampling both help with stability, and that adding constraints to the loss can help with generalization to different initial conditions. Also, I didn't present this, but if you check out the paper, you'll see we did another experiment with varying the box sizes and found that augmenting the data set of training data to include a variable range of box sizes could help generalize to even larger range, but that generalization quantitatively was still really hard with different box sizes. So we really will conclude here that generalization remains a key challenge for these particular types of simulators, especially. So moving on to part two of the talk, I'm going to talk about some of our work using learned models for inverse design. This is joint work with Kelsey Allen and Tatiana Guevara Lopez. And it's been absolutely wonderful working with these two, and they're really brilliant collaborators. The high-level motivation for this project is that we would really like to have machine learning methods for inventing new things that could interact with our physical world. Designing physical objects that serve some purpose, be it infrastructure changes like designing irrigation systems or transformative technologies like airplanes, has really allowed us to change the world that we live in. And it's something that if machine learning could help with, that would be just really cool. It's also a hallmark ability of humans to be able to rapidly and on the fly engineer or just design simple new objects that transform our everyday, or even something that we enjoy doing and will perform in the context of physics-based games. So we introduced a couple of different domains that are representative, we hope, of these different types of challenges. And the key question we're interested in is if learned simulators could be used to solve challenging physical design problems. To outline our general approach, first, for evaluating a design, we first parameterize some design space and then map these parameters onto the initial scene of some model that some model will operate over. So that's our initial scene. And then we apply a learned simulator to produce a rollout over up to several hundred steps. And then at the end of this rollout, we'll end up with a final scene and we'll evaluate the reward on this final scene. So in this case, the reward is, can you get the fluid into the blue circles? Then across design iterations, design parameters will be optimized so as to maximize reward. So we'll start out with a design that's not very good, and gradually these will be refined using some type of optimizer in order to make the design better. So to first outline what the model will look like, which is what's applying these iterations, we do task agnostic model training now with graph neural network-based simulators. So as opposed to the previous learned simulators, which used convolutional neural networks as their core processor, these are operating over graph-based objects. And there's a couple of reasons that we were interested in using GNN-based learned simulators. One is that, I'm going to try to load these builds all at once. One is that they can work for many different types of physics. They're efficient, they're accurate, and they're stable. They're also naturally differentiable because they're parameterized by neural networks. And this allows us to use gradient-based design optimization techniques, which will be useful for us. And then most importantly, perhaps, at least for design problems, these models have been shown to generalize pretty well. So this is previous work that was produced by some of my colleagues. And they found that you could train these models on pretty small examples of training data. So in this case, the inset panels contain images of the training data, and you can see like literally they're just much smaller. They're much smaller domains, but then you can take this same simulator and apply it to a much larger space, potentially with really complex and qualitatively different dynamics, but where the same local rules apply. So here we have a much more sophisticated ramp situation at the top, whereas at the bottom, we have a much larger flag that the same model can apply to. And this is particularly important for design optimization problems because your optimal design is not necessarily going to have been in your training data, and you want your simulator to not break when you start getting into those optimal regions of the space. You also don't want your optimizer to just take the model into a part of the space where it behaves incorrectly and unreliably and can hallucinate really good reward for itself that's just diverging with the ground truth simulator. So what this lets us do in our case is to pre-train a simulator on next step prediction using training data that's qualitatively different for the scenes that are encountered during design. So on the left, we have an example of the training data, and then these are a couple designs that we're going to get to in some of our tasks that you can see have really different dynamics overall, but the local rules are still intact. And this is what the learned models are operating over and therefore should be able to preserve. That's the model. And I'll also talk about the different optimizers that we used in order to refine our parameters. There's a couple different approaches to design optimization that are used in the literature. One that we can use because our models are differentiable is gradient-based optimization using our learned models. As our representative approach for this, we're going to use the Atom optimizer, which is a very popular and widely used optimizer that most of you are probably familiar with. And then another approach we can use is sampling-based optimization procedures, which make no requirements on the model that they use. It doesn't have to be differentiable because you're just going to sample different options and then input them into whatever simulator you have. So our representative for this will be cross-entropy method, which is a method that's really popular for model-based optimization. And then finally, we won't use this for all environments, but when we're looking specifically to see how well these models do for engineering applications, we'll look at gradient-based optimization using handcrafted models. And for this, we'll use Defoam, which is a specialized aerodynamics solver. So for our first domain, we're going to look at how our designs fare in 2D fluid tools environments. And what we find is that gradient-based optimization is capable of finding smooth and accurate designs compared to the sampling-based approach, although both of them can solve the problem in this framework. We find that this holds up quantitatively too. And interestingly, we also see that if we use a sampling-based approach with the ground truth solver, which is not differentiable, but is possible because sampling-based methods only need black box models, then we still outperform the sampling-based approach with this gradient-based methods because gradient-based optimization is so powerful. But of course, the ground truth has an advantage over the learned model for sampling-based methods. If we push the dimensionality of the design space and go to 625 dimensional spaces where we're optimizing the height of some landscape, we find the sampling-based approaches become really intractable and are not capable of finding good solutions at all. And then we looked at the problem of airfoil shape optimization to see how these models do in a task that's representative of something requiring more engineering level precision. And we find that we get comparable designs to the specialized Defoam solver in a fraction of the time. So this is the Defoam solver solution. And if we look at the solution produced with a model, this is what it looks like. And so you can see it looks kind of similar. It still has the S shape, but it's a little different. So to really push the accuracy on this, we use simple tricks like model ensembles which can yield an extra level of accuracy. So notice this looks a little bit more like the original Defoe model, doesn't have the blunt tip, and it has a stronger S shape. And we see that this holds up quantitatively as well. Here we see the accuracy of a single model compared to Defoe. And here we see the reward of an ensemble model, which is much closer. And then our final result that I'll show to you is that we see stable gradients over what we found to be surprisingly long rollouts. So these are 75, 225, and 300 time step runs. And we find that the accuracy of the gradient-based approach keeps improving for a really long time, up to 275 time steps. And so this means that not only is the forward pass stable for a really long time, but gradients are also, useful gradients are being passed through hundreds of time steps, as well as on each time step, tens of message passing steps in the model itself. So our conclusions for part two. First, we were very encouraged to just see that GNN-based learned simulators can support general purpose design over a variety of challenging physical domains. These problems have high dimensional complex state spaces and design spaces, and we can see useful gradients over hundreds of time steps. We see that task agnostic training on data that is out of distribution still can support useful design, and that's encouraging and not to be taken for granted with machine learning methods. And we also see that we can match the accuracy of specialized solvers and obtain solutions more efficiently, which is really encouraging. So in terms of some of our next directions, one thing we're really excited about is just across the board for both learned simulation and also learned simulation with the aim of design, that we want to have new domains that have challenging types of physics that can represent new and useful benchmarks to challenge machine learning. I think simulation is a very nice batch of inspiration for benchmarks in general, even if you're not interested in a particular brand of engineering application, because they're so challenging and because they're so diverse. You don't have this problem of everybody really like coagulating around a single problem. In the design space, we're really interested in exploring more robust optimization procedures. Gradient-based methods don't work for everything. They really struggle with zero gradients or noisy gradients, and local minima can provide a problem, whereas sampling-based methods have trouble scaling to these large spaces. So we're interested in new optimizers that are more robust, as well as new models of the dynamics and design spaces that are perhaps better optimized specifically for design instead of prioritizing accuracy on the forward pass, which has usually been our approach. And we want rich models of the design space that can support hierarchical, rich, perhaps compositional design. My favorite example of this is the schematic of an espresso machine. This schematic of an espresso machine that shows a really complex creation that you can design by getting simple parts together, which themselves have their own eccentric shapes and unusual designs to create something really complicated that creates something else that's really delicious. So thank you all for your time. I want to thank my collaborators. Kelsey Allen and Tatiana Guevara-Lopez were, again, co-leads on the Inverse Design project, and were wonderful to work with, as well as Toby Pfaff, Alvaro Sanchez-Gonzalez, Jessica Hamrick, and Pete also worked with me on that project. Alvaro was also a key collaborator on the Turbulence project and did a lot of work on that and was the senior author. So thank you for that. And collaborators at Flatiron, Google Research, and of course, colleagues at DeepMind. And thank you for your time.
Thank you very much, Kim.